Similarity dimension worked well for fractals that were perfectly self-similar because we could scale them down and see how many copies of themselves we needed if they were scaled by that amount. But for fractals that are not self-similar, we need to come up with a different notion of dimension. For box dimension, we're going to cover our particular set in boxes that are of size epsilon, and the number of boxes that we need is n of epsilon. What do I mean by box? Well, if our set S is a subset of the plane R squared, then use boxes that are squares. And if it's a subset of 3 space, then use boxes that are cubes. We will find that the number of boxes needed scales with the size of epsilon, and it's going to scale via this power law that involves a number d. That d is our box dimension. Specifically, if the limit exists, d is the limit, as epsilon goes to 0, of the natural log of the number of boxes as a function of epsilon divided by the natural log of 1 over epsilon. As a first example of box dimension, let's look to the Cantor set. The Cantor set lives within a segment of the real line, and so the boxes are going to be line segments. Consider the class of epsilons where epsilon is 1 over 3 to the n. So if you remember the way that we made the Cantor set, it was like this. And so we need, if epsilon is 1/3, we would need 2 boxes. And if epsilon were 1/9, well, all the points in the Cantor set fall within these intervals that are still there. And so we would need 2 squared boxes. And if it were 1/27th, well, we would need 2 cubed boxes. And etc. If it's 1 over 3 to the n, we need 2 to the n boxes. Okay, so we need 2 to the n boxes, and now let's figure out our box dimension based on this. Epsilon is going to go to 0 as n gets big, so instead of the limit as epsilon goes to 0, we want the limit as n gets big, and we want the natural log of the number of boxes, which is 2 to the n, divided by the natural log of 1 over epsilon, which is 1 over 1/3 to the n. And simplifying, this is natural log of 2 to the n over natural log of 3 to the n. We can bring out the n's, and they cancel, and so actually we end up not needing to take the limit, and we get the natural log of 2 over the natural log of 3. This is the same dimension that we got through our self-similarity measurement, so this box dimension definition for this example so far is consistent with our previous notion of defining dimension. Let's construct a fractal that's not self-similar for our next example. So let's put ourselves in R2, and we take a box and we split it in 4, and we keep 3 out of the 4, but the one we discard is random, which is going to eliminate our self-similarity. So then we divide each of the boxes we've kept into 4, and we randomly choose which 3 we keep. And as we repeat this process, you should see that we're getting a fractal for sure, but it's not self-similar. When we say a box has size epsilon and we're living in 2D, we're going to be referring to the length of its edge. And so let's think about boxes. Let's say that our original side was 1, and when we broke it in, this was length 1/2, and this is length 1/4. And so the nicest epsilon that we could think of here is epsilon is equal to 1/2 to the n, because those are nice length sides for covering our boxes. And if we chose 1/2, you can see that we need 3 boxes. And if we choose 1/4, it looks like we need 1, 2, 3, 4, 5, 6, 7, 8, 9 boxes. And if we choose 1/8, we need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27 boxes. And that's because each time we split into 4 boxes and we keep 3 of them. And so our number of boxes goes up by a factor of 3. And this relationship is enough information to compute our correlation dimension. So our dimension is the limit as n goes to infinity of the natural log of the number of boxes divided by the natural log of 1 over epsilon as it varies with n. And that gives us a natural log of 3 over natural log of 2. This is greater than 1 and it's less than 2. And it's definitely within what we would expect given that we're not filling the 2D space as we create this fractal structure, but its dimension's definitely bigger than 1, so this looks perfectly reasonable. There are some challenges to using box dimension. In the examples we just looked at, they were constructed in a way that it was designed to work out very nicely, but it doesn't always work out in practice. It can be computationally intensive to use a range of different epsilons and mesh your boxes and figure out how many of them you need. Another drawback is that the box dimension isn't always right. It doesn't always give you something that seems reasonable. For example, if we consider the rationals in the interval 0, 1, okay, I need to draw in a ton of points, but they're a countable set of points, as we argued earlier, but in order to cover them with boxes, they don't have that much nice structure, and so in order to cover them with boxes, we actually end up getting dimension 1. And that's just because there's not a lot of structure going on, but there's not that many points, it's a countable set, and so their dimension really shouldn't be 1. That doesn't fit in with our notion of dimension, because we think of things that are dimension 1 as being actually parameterizable as continuous, and there's no sense in which this countable set can be parameterized as a nice continuous set. It should definitely have dimension less than 1. Now that we have a couple of notions of dimension and some intuition about the idea of fractional dimension, soon we're going to try to apply the idea of dimension back to dynamics and the chaotic systems that we're thinking about.